Hi, welcome back. So today we'll be still looking into chapter 16 on waves. So last time we brought the concept of wave, which is the disturbance that propagates, moves from the place it was created. Okay, so water waves or the gravitational waves or the electromagnetic waves, they are all waves. And the focus of this chapter will be on mechanical waves. So in mechanical waves, there are two types of mechanical waves: transverse wave and longitudinal wave. So in a transverse wave, the median moves up and down perpendicular to the direction of wave propagation. In a longitudinal waves, the median oscillates back and forth in the same direction as the wave propagates. Okay. So for wave, there's these quantities that we use to describe the waves, the wavelengths, the amplitude of the median oscillating, the period of the wave, and the speed of wave. Okay, so speed of wave will be lambda over period or lambda times frequency. The mathematics of waves, we look at that last time as well. So the wave function is a function of the position as well as the time t. So you can write as f in the function of x minus vt in this case, then the wave propagates in the positive x direction. You can also write in another way, f equal to x plus vt. So in this case, then the wave moves in the negative direction. Or in terms of wave numbers and angular frequency, so the y as a function of x and t should be equal to a sine or cosine function, doesn't matter. They are just a shift of each other, okay? So sine of kx, where k is equal to 2 pi over lambda, that's called the wave number, and then omega is equal to 2 pi over t. T is period, which this is the omega is the angular frequency. If you have, again, here, the minus sign here in the sign argument, then the kx minus omega t, then the wave is propagating in a positive direction. If there's kx plus omega t, then wave is propagating in the negative x direction, okay? So by using wave number and angular frequency, you can also calculate the speed of wave, which will be the angular frequency over the wave number, omega over k. In general, your wave could be also a sine, cosine function or sine function, doesn't really matter, but in general, you might start with an initial position, initial phase that's not exactly a sine or cosine function. So you have initial phase shift phi in the sine or cosine argument. Of course, if you incorporate the x here, so that would be kx minus or plus omega t plus phi. Okay, so in general, your y as a function of xt, position and time, is equal to an amplitude sine of kx plus or minus omega t plus phi as the initial angle phase or phase initial phase in that sense. Okay, initial phase shift, you can call it that way. So if you have the wave function as a function of x and t, then you can calculate what will be the speed of the medium vibrating by taking the partial derivative of the y with respect to t. So dy dt, yeah, basically, right, gives you velocity in that sense. And do the double derivative one more time, they'll give you the oscillation of the medium vibrating, okay? And because of that, that you can take a double derivative of the wave function with respect to t square, so you get oscillation, okay, which is a sine function if you start with y as a sine function, okay. Now, if you do slope of the wave, that's doing the partial derivative of the wave function with respect to the position x. That gives you a slope. If you do it double derivative of wave function with respect to x, it gives you curvature of it. So looking at the result here, these two are both sine functions, so they are related to each other, okay? So if you set these two, because this is sine and also sine, so you can rearrange the term, right? Take this minus a omega to this side, and then take ak to this side. So when you set then the sine equal to either this over minus a omega t, or either this guy or here, this guy over minus a k square, okay? So then you get this as a result, also taking account v equal to omega over k. So then partial derivative of y with respect to x square is equal to 1v squared partial derivative of y over partial derivative of t squared. Okay, so that's a linear wave function. This is also, we have seen this for the EM wave, which the EM in that case, partial derivative of either the E or M or the B, electric field or magnetic field, right? With respect to position square is equal to 1 over epsilon naught times mu naught square, right? So times partial derivative of the E or B as with respect to partial t square. In that case, we get the speed of light to be equal to epsilon naught times mu naught and take square root of that. Happen to be 300 million meters per second, okay? All right, so today let's take a look further look at the speed. What's the determining factor for the wave speed on a wave in the stretch string? Okay, so if you have the string for tau, taut, then there's a tension in the string. Okay, so we had done this lab, so we know that the so we have like experimental study this, right? We came to the conclusion that the wave speed is determined by two factors. One is the tension in the stream, which like we vary weights, right? If you remember that, the second one will be the mass of the string, which gives you the linear mass density of the string, right? So that's the other quantity that we had to determine. So as the tension in the string increases, the speed of wave actually increases as well, okay? So in this case, and for the dimension of the mass per unit length, we do mass divided by L to give you the mu, right? For the mass per length, which is the mass density. So the speed V is in a function of two factors, tension and mass per length. So let's take a look at the dimension here and then the units. So velocity, right? That should be in meters per second. Force should be equal to Newton's time, which is equal to, according to Newton's second law, so mass times acceleration, kg times m over s square, second square. And mu as the linear mass density, which is kg over m. So V is a function of this guy and then also this guy. So let's write this as this, right? V equal to F to a power times mu to another power, A and B, okay? So in this case, on the left-hand side, the velocity should have a units of meters per second, right? Force is kg times meters over second square to the I's power, and then kg over m to the B's power, okay? So looking at the right-hand side here, we know that then you will have kg to the A plus to the B, right? And then meters to the A but minus B because meters is in the denominator on the second term. The second will be then have a power of, because it's in the denominator, so minus 2a, okay? So that's the dimension you get from the right-hand side equation. So these should be equivalent to this guy, right? So then that tells you, because on the left hand, you don't have kg. So that tells you first, a plus b should be equal to 0. So then kg becomes 1. Kg to the 0 becomes 1, right? You should have meters there. So that means a minus b is equal to actually 1. This is just in the denominator. So this means s to the minus 1. So minus 2a is equal to minus 1 or 1. Okay. 2a equal to 1 because that's minus 1. So then we get those three equations. Let's write them down on the paper. So the first one we have give me a second, let me adjust my screen here. Okay. So if you look at the PowerPoint slide, right? So on the kg term, kg to the a plus b, that should equal to 0. and then m to the a minus b, that should equal to 1. Minus 2a should equal to minus 1. Or actually, yeah, minus 1. That's right. So 2a equal to that, to 1. So this tells you, okay, a then equal to 1/2. Okay. So then if a equal to 1/2 from here, we should know then b equal to minus 1/2, right? And that fulfill this relationship because positive 1 minus 1 becomes 0. Okay, so then we get, okay, then a equal to 1/2, b then equal to minus 1/2. So then v as a function of a to f to the a, and then mu to the minus half, right? So that should be square root of just the force over mu. All right, and then that's also we had in the lab. So this then gives you, okay, speed then in terms of tension over mu. That's the equation or the final relationship for the speed of wave in the string under tension. Okay, so it depends on the tension. It also depends on the linear density. Okay, so let's go back to the slide. Okay, so then the result is V equal to then square root of F being tension in the string over mu linear mass density. Okay, let's take a look on one example here. So this one says you have two guitar strings made of steel, have the same length. String A has a diameter of 0.50 millimeter and is under 410.0 tension. String B has a diameter 1.0 millimeter and is under tension of 820.0 newtons. Find the ratio of wave speeds, VA over VB, in these two strings. Okay. So we got DA 0.50 millimeter. We got DB 1.0 millimeter. We got tension. Let's use F. In A is 410. We got FB is 820. Okay. They are both made of steel. Steel guitar string. Okay. So they are made of the same materials. All right. So we are looking for VA over VB. And we know VA should be equal to square root of FA over mu A, right? Mu A is the mass of the A string A over the length of it. All right. So let's do this. The mass of A, and let's do down here, let's do the cross-sectional area pi over 4 dA squared, right? This is cross-sectional area times L. So that means on the top, we will also do that, right? Multiply by that. So this gives you volume, okay? Mass by volume, that means the density, right? Density of the steel times pi over 4 dA squared, right? So the rho of the steel times that. We can do the same for mu of B, right? So mu of B should be mass of the B divided by L, the same length. So the same thing that we did to that guy, pi over 4 of, in this case, B dB squared times L. Okay, so this mass divided by that, that's also the density, volume density, but it's made of steel. So this is the same, okay? Pi over 4 and then dA squared, dB squared, okay? So we actually have related the linear density to the density and the cross-sectional area, right? And then also here, the same thing. So VA over VB, then it's really square root of FA over mu A, right, divided by square root of FB over mu B. Okay, so which is, let's do FA, which is 410, so square root of 410 newtons over, this guy will be rho of the steel, right, times pi over 4 dA square. Okay, so this is what we have on the top. At the bottom, we should have 820 newtons over rho steel times pi over 4 dB squared. Okay, all right. So then look at this. There should be some cancellations, right? Steel will cancel. Pi over 4 and pi over 4 cancel, right? 410, 820. So this is twice of that. So this guy and this guy will cancel. So I have 2 here, but 1 on top. Okay. So now we should have just in this case, dA square is in the denominator, right? So this is also in the denominator, but under the denominator. So this should flip up, okay? So it should give you now VA over VB now should equal to such square root of dB square over dA square. And the 2, it's down here, so 2 there, okay? All right. Now we can take a look at dB and dA. So dA is 0.5, dB is actually 1. Okay, so 1 over 0.5, that gives you 2, right? 2 square divided by 2. So that means 4 divided by 2, right? So that gives you square root of 2, okay? That's your result. Okay, so VA is square root 2 of times of VB then. All right. So there's a trick here we had to do, just because they are made of the same material, so that means their volume density is the same. Their linear density is not necessarily the same because the thickness is different. Okay, so linear density is related to the volume density times the cross-sectional area. Okay. All right, so let's go back. Next section here talks about energy and power in waves. So when earthquakes hit, right? So there's oftentimes devastating consequences. That is because earthquakes, as waves, carries a lot of energy. So when that wave hits a city or a certain area of community, then it will bring damages to the buildings, etc. Okay, because the energy hit. So let's take a look on the energy in the waves, okay, in the mechanical waves. So because the medium vibrates, going up and down, so there's velocity, right? So then there's a mechanical energy, right, or kinetic energy there. So kinetic energy, if you take the portion of the stream here on the wave, so delta m, so it should be equal to delta m, 1/2 delta m times v squared, right? So kinetic energy in this case, if this is a linear mass density mu, so delta m then equal to mu times delta x, okay? So equal to that guy. In derivative form, then you do derivative of k equal to taking the limits of x equal delta x equal to 0. So then that will be delta x, or derivative of x, okay? Mu derivative of x, vy squared. Now, y is equal to a function of, let's take a sine function. So then the vy will be a cosine function, okay? So then dk equal to 1/2 the mass, okay, times the velocity squared. Okay, so at the end, that portion of the string carries of energy of 1/2 mu dx. Okay, a squared omega squared cosine of the function kx minus omega. Okay, so you can see the energy is proportional to the amplitude. Also frequency. Okay, so if it vibrates more frequently, then it has more energy. Okay, so that kind of makes sense, right? So energy is proportional to the amplitude as well as the frequency, And then also, of course, the linear density, right? If linear density is heavier, then the energy will be more. All right. So when you have energy carried by wave, in this case, if it hits certain area, right, over time t, we know that gives it density. So density, intensity, wave intensity equal to energy divided by A times t. And because E over T is power, so then the intensity it can also be expressed as P over A. So in that case, the power of the wave divided by the area gives you the intensity at certain point. So the SI unit for intensity will be for power, it's watt divided by area will be meter square. Okay, so I equal to P divided by A. Now, a lot of times a wave comes out as a point source, so then it propagates 3D dimensionally in the radial direction outward. So the area at certain point r distance away then will be the spherical area, right? So the 4 pi r square. So I equal to P over 4 pi r square. So in fact, like animals such as bats, they give out sound waves, and then depending on the intensity comes back from the insect, they can tell how far the insects are located and then in which direction, so they can chase and hunt for the insect in that sense. Okay. All right. Let's take a look on sorry, clicking too many. The example here. So it says a sound speaker is rated at a voltage of V equal to 120.00 volts and a current of 10.00 amps. So if you have V and I, you can calculate the power of it. Okay, so power of it equal to voltage times current. Electric power consumption is P equal to I times V. Okay, so just like the equation says. To test the speaker, a signal of sine wave is applied to the speaker, assuming that the sound wave moves as a spherical wave and that all the energy applied to the speaker is converted to sound energy. How far from the speaker is the intensity equal to 3.82 watts per meter square? All right, let's take a look. So it tells us we can calculate power by using P equal to I times V. So we can calculate power first. Power is VI 120 times 10. So that gives us 12,000 or 1200 watts, right? Now it's asking you F my intensity. So this is for intensity, okay? So I intensity equals to power over area. And this is spherical area, so P over 4 pi R squared. It says if this guy equals 3.82 watts over meter square, then what will be the R, right? So 1200 watts over 4 pi R squared. So you simply just solve for R, okay? So R then equals to 1200 watts over 3.82 watts per meter square, and then 4 pi here, and square root, okay? So that turns out to be 5 meters. All right. I think we will just stop here for today, and then we'll come back for the next sections later. Okay, so see you guys.